we shall learn simultaneous measurability of observables, that is, compatible observables, commuting observables. If two operators commute, then both the quantities can be measured at the same time with infinite precision. That is, commutator A, B equals 0 implies that AB equals BA. But in quantum mechanics, it is not possible to measure two non-commuting observables simultaneously to an arbitrary accuracy. Here, X, P, they are incompatible observables, non-commuting observables, which is equal to IH class. If two operators commute, then they have same set of eigenfunctions. By definition, two operators A and B commute if the effect of applying A then B is the same as applying B then A. That is, AB equals BA. If two operators commute and consequently have the same set of eigenfunctions, then the corresponding physical quantities can be evaluated or measured exactly and simultaneously with no limit on the uncertainty. In addition, in quantum mechanics, the configuration of a particle is fully defined by its wave function. When a measurement of a particular observable, for example, position, angular momentum, and so on, is made on the particle, its wave function will collapse to one of its eigenstates of the operator used to represent the observable whose corresponding eigenvalue gives the result of the measurement. The following two theorems indicate the connection between compatible observables and commuting observables. Theorem 1. If A commutes with B, then they will have a common eigenfunction. For example, we'll consider operators A and B with a common set of eigenfunctions because they commute. So we'll take the wave function psi I, where I equals 1, 2, 3, 4 goes on. And we know that eigenvalue equation A operator operates on psi A will give us eigenvalue AI psi I. Similarly, B psi I equal to BI psi I. Then we'll consider AB psi I, which is equal to, we keep A operator as it is, B operator operates on psi I will give us BI psi I. BI is the value, you can pull it out. So BI, A operator operates on psi I. Now we know that A operator operates on psi I will give us AI psi I. So BA and AI are values we can interchange, we can write as it is AI, BI psi I. Now we'll consider BA psi I. So BA psi I, keeping B as constant, A operates on psi I will give us small ai psi I. A is the eigenvalue, you pull it out. So AI, B psi I. And B operator operates on psi I will give us BI psi I. So this time we have AI, BI psi I. And look at the left hand side, extreme left hand side, AB psi I, which is equal to BA psi I. We know that they commute with each other. So AB psi I, which is equal to AI, BA psi I. BA psi I, that also is equal to AI, BI psi I. So we can say that AB psi I, which is equal to BA psi I. So it implies that AB minus BA equals 0, A comma B equals 0. So A commutes with B. Now we'll go for theorem 2. Commuting operators will have common set of eigenfunctions. We know that the eigenvalue equation A psi I equal to AI small ai psi I. Operating both the sides from left by B. So BA psi which is equal to B. A operator operates on psi will give us small a psi I. So we can write like this. Now, since AB equals BA, we can write BA as AB psi I. So B operator operates on psi will give us now BAI psi I. So AB psi I, we know that which is equal to BA BAI psi I, since AB equals BA. Now look at this A and this is B psi I, which is equal to, you can pull AI out. So AI, So this is nothing B psi I. Here, put together B psi I and right hand side also we have B psi I. So it implies that B psi I is an eigenfunction of A with the same eigenvalue AI. Since B psi I equals Bi psi I, B psi I can differ from psi I only from the multiplicative constant Bi. So psi I is a simultaneous eigenfunction of both A and B. Now let us learn general uncertainty relation. We know that the uncertainty relation goes like this: del x, del px greater than or equal to h bar. Here we are talking about two canonically conjugate variables. Two canonically conjugate variables means they will be inserted some properties. They will be connected with some properties. And these two variables cannot be measured simultaneously accurately. Here, del x stands for uncertainty in the position and del px stands for uncertainty in the momentum. Del x can be interpreted in terms of standard deviation. Del x is nothing but a spread. So we can't have a specific value. X, we can't have a specific value, even though because they are all quantum particles are connected with the wave function. So still there will be some spread. It states that any two canonically conjugate variables cannot be measured simultaneously and accurately. Two dynamical variables cannot be measured simultaneously and accurately in quantum mechanics. For example, position and momentum. Similarly, energy and time. So it is defined as del x, del px greater than or equal to h bar. Similarly, this is for the Cartesian. You can also go with del r, del pr greater than or equal to h bar. We can also go with simultaneous pairs in polar coordinates. But del x, del py equal to 0. We can measure simultaneously del x and del py. This is in the other direction. Similarly, x with the pz, that also can be measured. So incompatible observers, here compatible observers. So now we'll go with this diagram. Here, this is a uniform wave function. So we have uniform wave function here, and distance between two crest and two trough will give us lambda. And of course, from de Broglie relation, lambda equal to h by p. If lambda is known, p is known. So momentum is well defined here. What of the position? Position of the particle usually considered as the highest point in any wave. So this is our highest point. Here also it is highest point, but it varies from minus infinity to plus infinity. See, it goes from 0 to plus infinity. So position can be anywhere with the amplitude, the highest amplitude, because it goes from 0 to infinity. The position is poorly defined. Where we are going to take the position? Anywhere we can take. So position is ill-defined, whereas momentum is well-defined. Now, that's the reason that the wave packet has been introduced. Here in the wave packet, the highest point is here somewhere, and another one highest point is here, which varies with some degrees. And here we can say that position is poorly defined. What of the momentum? That also ill-defined, poorly defined. And group of waves which are consecutively present here where the particle is present. And group of waves which are destructively interference, there is no particle at all, poorly defined. So we can say that position and momentum are poorly defined. Here in the wave packet, where the superposition of all wavelengths will interfere. Where the particle is present, then there will be consecutive interference. Where the particle is absent, there will be destructive interference. So this is the illustration of wave packet, which is nothing but uncertainty principle using. Now consider this way. So we are going to consider this a uniform wave, and we are going to superpose with another wavelength. It's a green color, exactly like this. And these two waves, they superpose here. And you just look at the center, both the waves merge together in phase. So here it is in phase, but here it is out of phase, and here also it is out of phase. And this diagram can be exactly correlated with the wave packet. So where the particle is present, we have a maximum amplitude. Where the particle is absent, we have minimum amplitude. And this is called our del x, the spread in position. And this is nothing but your wave packet, superposition of many waves here. So the envelope is nothing but our group velocity, which is nothing but your particle velocity, but the waves inside is nothing but your phase velocity. So there is an uncertainty in wavelength as well uncertainty in position. So this is the another illustration of uncertainty principle. Now the technique of uncertainty principle has been taken from the Fourier transform. We know that the wave packet is defined exactly like this. The Fourier transform of this is nothing but this. So Fourier transform is momentum space. What we call this is state space. And this is the wave packet is somewhat broader, whereas the Fourier transform, this is somewhat narrow. Just consider this, the wave packet is very narrow, whereas the Fourier transform of this wave packet is nothing but broader. So here it's broader. So just opposite in nature. So we want to measure in del x, and del k will be spreading over. If we want to measure del k clearly, then del x will be broader. And it can be shown by standard mathematical methods, del k greater than or equal to 1 by del x. And we know that the wave vector k is defined as 2 pi by lambda, and del k is nothing but 2 pi by del lambda. We know from de Broglie hypothesis, P equals h by lambda. So del P equals del h by lambda, which is equal to h divided by, instead of del lambda, we can substitute 2 pi by del k. So h divided by 2 pi del k. H divided by 2 pi is nothing but h bar del k. So del P equals h bar del k. So therefore del k equals del P by h bar. We know that del k is greater than or equal to 1 by del x. So instead of del k, you can substitute 1 by del x. So that gives us del x del P greater than or equal to h bar. This is one way of deriving the uncertainty relation. Then another way is E equals P squared by 2m. So differentiating that will give us del E equals 2P del P divided by 2m. 2 gets cancelled. We have P del P divided by m. And of course, we know that P equals mb del P by m. M gets cancelled. So we have del x del P by del T. And del x by del T is nothing. And therefore, del E equals del x del P by del T. But del E equals del E multiplied by del T, which is equal to del x del P. Just now we derived that del x del P is greater than or equal to h bar. So we can say that del E del T, which is equal to del x del P greater than or equal to h bar. Uncertainty principle for position and momentum, which has been clearly derived from wave packet description. Now further we can define like this. X is the displacement, which is the integral multiple of lambda. So we can have del x equals n lambda. From de Broglie relation, del x equal to n lambda. So lambda is nothing but h by p. So n multiplied by h by p. Also from the waves, lambda equals n times del lambda. So n equals, we know that n equals lambda divided by del lambda, and use de Broglie relation, we can have p divided by del p. So substituting here, so we know that del x equals n h by p. So we can substitute for n here. N is nothing but p by del p. So p by del p multiplied by h by p. P gets cancelled. You h divided by del p. Cross multiplying will give you del x del px, which is equal to h. Since the waves are irregular in the wave packet, we can write del x del px greater than or equal to h bar. And we said that this del x is uncertainty in the position, and del px is nothing but uncertainty in momentum. The moment when you are going to measure del x, the del px will be very larger. The moment when you are going to measure del px, and del x will be very larger. This is exactly depicted in the figure. So look at the picture. This is del p versus del x, and it shows the rectangular hyperbola. When del X is very larger, del P will be very smaller. When del P is very larger and del X is very smaller, the minimum uncertainty occurs exactly here. So minimum uncertainty exactly occurs here. And this is nothing but the del X, as I said, the spread, which is nothing but in mathematics, this is nothing but standard deviation. So variance, or another one is square root of the variance. So there is no sharp value and there will be a small spread will be there. And this is exactly connected with the probability distribution. And del X standard deviation is connected with the probability distribution we are talking about. But here we have any quantum system is connected with the psi. So psi is nothing but probability amplitude. The solution of probability amplitude from Schrodinger equation one can derive. So equation 1.152 refers the uncertainty principle. Now let us solve one small problem connected with the uncertainty principle. So we are going to estimate the ground state radius of hydrogen atom and the energy of the hydrogen atom. According to uncertainty principle, we know that del R del P is more or less equal to h bar. So for the time being, we'll have R times P more or less equal to h bar. So we'll have P which is equal to h bar by R. And we know that E of R, which is nothing but kinetic energy plus potential energy. And potential energy is negative, that's why minus E squared by 4 pi epsilon naught R. And in terms of de Broglie relation, we can write P equals h by lambda, but here it is P equals h by R. We can write this as minus h bar squared divided by 2m E R squared minus E squared by 4 pi epsilon naught R. Now just minimize the electron proton radius, that is dE by dr, which is equal to 0. So differentiating this will give us, the R squared will go to the numerator, will have minus 2R to the power 3. So that will give us minus h bar squared divided by me R naught cube. So now R becomes R naught here. And 1 by R will give us minus 1 by R squared. So this becomes plus E squared by 4 pi epsilon naught R squared. So bringing this term to this side, we'll have minus sign will get cancelled. We have h bar squared divided by me R naught cube, which is equal to E squared by 4 pi epsilon naught R naught squared. Here R naught squared and this R naught cube will get cancelled. We have remaining one R naught is left out. So cross multiplying will give us R naught, which is equal to 4 pi epsilon naught h bar squared divided by me squared, which is equal to 0.53 angstrom, which I have done it here. So I have substituted the values here. 4 multiplied by pi stands for 3.14, epsilon naught 8.85 10 power minus 12, h bar squared, which is nothing but h divided by 2 pi, that will give us 1.055 in 10 power minus 34 whole squared, divided by mass of the electron and the charge of the electron. So I have simplified and it is in terms of meters. Now we can get in terms of angstrom here, which is nothing but 0.55 angstrom. So now let us go for the second one, energy of the hydrogen atom. Energy of the hydrogen atom is defined as exactly like this. Now we have already obtained the value of R naught. You substitute here, we will get exactly minus 13.6 electron volt. And minus sign shows that it is a bound state.